Welcome everyone to week 8 of our NPTEL-PMRF problem solving sessions, Electronic Theory of Solids. A brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Solid State and Structural Chemistry Unit SSU of the Indian Institute of Science IIC Bangalore, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL-PMRF TA for this course. Alright, so let us start today's session. Just let me just check. Alright. Can you just check? Alright. So first we will start with the problem number the problem that we left in the last session. So it was problem number 9 of last session. So the problem is we have to consider a model 3 dim. Okay, just 1 minute. Okay. So let's start with our problem number 1. So this is the last problem that we left in the last session. So the problem is, consider a model 3-dimensional lattice of spins, each with spin s equals to half. Okay. So first we have to calculate what is the magnetic moment of each spin, and what are the allowed values of the projection of the magnetic moment mi onto some chosen axis, say C. Okay. So let's just do part A first. So in part A, so basically what we have to find, part A we have to find, we have a system, basically we have 3-dimensional lattice of spins, and with each spin having s equals to half, and in the first part we have to find what is the magnetic moment of each spin, and then what are the allowed values of the projection of the magnetic moment mi onto some chosen axis. So basically this is what we get if we apply a magnetic field. So so we generally choose it to be along the z axis. So first we have to find a magnetic moment on each spin. So remember that the magnetic moment remember that the magnetic moment of the total magnetic moment. So we are solving this problem from the last problem from our last session. Please mute yourself if you don't want to ask any questions, otherwise it will be from where the sound is. Alright, okay, so we are doing this problem. This is problem number 9 from our week 7 last session. So this we were not able to solve in the last session. So again I'm repeating the problem. So first of all we have to consider a model 3-dimensional lattice of spins, each with spin s equals to half, and then in the first part, what we have to do, we have to find what is the magnetic moment of each spin, and what are the allowed values of the projection of the magnetic moment mi onto some chosen axis, which is basically when you apply a magnetic field. So all your magnetic moments, they will align in one direction, and we generally consider it to be the z axis. So you will see those things in other problems as well. So first we need to find the magnetic moment for each spin. So remember that the magnetic moment of the total the magnetic moment of the total magnetic moment of a spin, the total magnetic moment of a spin s is equals to Ge mu b under root s into s plus 1, and the component along a specific direction is given by minus of GE mu B times MS. Alright, yeah. Alright, so this is our total magnetic moment, and this will be our magnetic moment in a particular direction. Now here G, and here this GE is the G factor of the electrons. Okay, this is the G factor of the electrons, which is equals to two. Okay, so we are taking GE factor to be 2. For electrons, G is around 2, and MS can take values of half and minus half, and mu B, that is the Bohr magneton, alright. So here first of all, what we have to find, we need to find the total magnetic moment of each spin. Where we have S equals to half, so this M total, that will be written as GE times mu B under root S into S plus 1. So G is 2, mu B, I will just leave it as mu B, Bohr magneton, and 1 by 2 plus 1. Okay, so if you calculate it, okay, so basically you will get M total equals to, that will be equal to root 3 times mu. Right. And the Raoult values of projection of the magnetic moment onto some chosen axis are, okay, and MS value, since S is equals to half, so MS value will be plus minus half. So basically our Mi here is minus GE times mu B times MS. Let me just check. Yeah, I'm not sure if this minus sign is correct or not. I have to check, but most probably I guess if the magnetic direction is given, then it's not. Yeah, I will check and get back to you in maybe in the next section. But basically it will be equals to okay. So it is basically the magnitude where it is G times UV times MS, and MS we have plus minus half, but MI is minus G. So accordingly we will have this magnetic moment in this particular, in a specific, let's say Z direction. We will have these values. minus mu b and plus mu b. Alright. Then okay. Then the B part. So the B part is what are the possible values of the magnetic energy of each spin? Okay. So the magnetic energy. So now it is asking what are the possible values of the magnetic energy of each spin. Now the magnetic energy is, we know, is given by, since the magnetic energy is E equals to minus m vector dot h vector, where h vector is your magnetic field, the applied magnetic field, the around magnetic energies in an applied field h vector of magnitude h r. So the energy value will be just whatever the minus mi times h. Okay, so this is the mi is the magnetic moment along this h direction. Let's say it is also in the z direction, and mi values we have already calculated. Okay, for ms equals to half we have minus mu b, and m square minus half we have plus mu b. So the energy values will be equals to this nu b times h for magnetic moment equals to minus nu b, and minus nu b times h for magnetic moment is equals to plus nu b. Alright. Okay. So this is the answer. So basically we can see that if the magnetic moment, they are aligned in the direction of the magnetic field, okay, where you have mi equals to nu b, then you will have, then those spins, they will have lower energy, their energy will be lower, then that will have a minus mu b times h, while the magnetic moments which are in the anti-parallel direction to the applied magnetic field, let's say the magnetic field is in h direction while the magnetic moment is minus mu b, then you have energy is equal to mu b times h. Alright. That's the thing. Then let's go part C. Okay, now assuming that the spins are non-interacting, okay, calculate the magnetization of the lattice of spins when a magnetic field H is applied, or okay, assuming that the spins are non-interacting, calculate the we have to calculate the magnetization of the lattice of spins when a magnetic field H is applied along the z-axis. Okay, so now we have to find what is the net magnetization is going to be. Now, so in this case, the partition function just 1 minute. recorded. Let's, okay. So okay, let's back to the problem. Okay, so we are doing part C. So we have to find the net magnetization when the magnetic field is applied in the z direction. Now in this case, the partition function, first we have to find a partition function. So the partition function is given by this z partition function. We know is given by summation of I e to the power minus whatever ei by kbt. Okay, so energy ei values we have already nu bh and minus nu bh. So the partition function will be minus nu bh by kbt plus e to the power nu bh by kbt. Alright, so and that we can write it as 2 times cos hyperbolic nu bh by kbt. Since so this is the formula. So we are going. So earlier also I have written. So we are going to use this formula a lot. So this is cos hyperbolic and the sine hyperbolic of x, that comes as e to the power x minus e to the power minus x divided by 2. Okay. So the average magnetization. Now we have to find out. So the average magnetization so the average magnetization per spin is summation of I mi as e to the power minus ei by kbt. So we have this. Okay, so now we have the z. Okay, let's keep it as z. And now we know for nu b, it will be e to the power the energy will be minus nu bh, so you will get a plus here. So you will have e to the power nu bh by kbt. Alright, and then plus for minus magnetic moment minus mu b, we will have energy e to the power energy is nu bh, so it will be e to the power minus nu bh by kbt. Alright, and you can just take mu b, you can take common here. Okay, but you will left with nu bh by kbt minus e to the power minus mu bh by kbt. Alright, and then using the sine hyperbolic formula as written here, e to the power x minus e to the power minus x divided by 2, we can write this mu b is written as 2 times sine hyperbolic nu bh by kbt, right? And the partition function we have already found, it is 2 times cos hyperbolic nu bh by kbt. Alright, and then basically from here we can find the net this average magnetization will be equal to nu b, and sine hyperbolic by cos hyperbolic is tan hyperbolic nu bh by kbt. This is our answer. So this is our average magnetization. So what we have found here is the average magnetization per spin, and the problem is we have to find the total magnetization. So the total magnetization M is given by, so the total magnetization M will be just equals to the this is the density, the total number of spins per unit volume, times whatever the average spin is, average magnetization is for each spin, for each magnetic moment. So basically then M will be equals to n nu b tan hyperbolic nu bh by kbt. So this will be our total magnetization. The final answer is this, where this is number of spins per unit volume. Right? Okay. And is the number of spins per unit volume. Okay. Then let's go to the part D. Okay, this was part C. Now part D is, for a given value of field H, how does the magnetization M depend on temperature? Okay, now we have to find the dependence of this magnetization on temperature. Okay, what the magnetization for given field H, we have already found the magnetization, and explain the behavior of M for T tends towards 0, taking the number of spins per unit volume, the small n value that is given to us, and calculate the numerical value of the saturation magnetization Ms at T equals to 0. Explain the behavior of M for T tends to infinity. Okay, so this is the D part. So we need to find how M will change with temperature. So for M formula we already have the relation of the temperature. Now we have to find basically the limit of this magnetization at T equals to 0. We know that there is no thermal fluctuation, so our magnetization will be saturated magnetization. It will be maximum magnetization within the applied magnetic field, and as we increase the temperature, the thermal fluctuations will increase, so we expect this magnetization to reduce. Alright, and so those limits we have to find. Now for a given field, the magnetization decreases from the zero temperature value of n times mu b to the, okay, so at zero temperature we will have the highest magnetization, and highest magnetization you can consider that all the magnetic spins, they are aligned along the this whatever the applied magnetic field is, so that is your highest magnetization. So that is just n times mu b. Okay, zero temperature value of n mu b to the high temperature value of 0. So at very high temperature it will tend to 0, as the temperature T increases, from zero to infinity. So now basically we have so this is here, so we can numerically see this. So this is our magnetization that we have calculated, mu b h by kBt. So this is what we have written, that is from the intuition. So basically we know that at T equals to 0 it will be, the magnetization will be highest, the saturated magnetization, which is n times mu b, and at very high temperature T tends to infinity. At very high temperature all the spins will just fluctuate, and because of this the net magnetization will be 0. Okay, it will be a complete paramagnetic system. Now for fixed H, now numerically also we can check this. For fixed H, basically as T tends towards 0, what will happen? Your tan hyperbolic mu b h by kBt, okay, which is basically what is it? It is e to the power x minus e to the power minus x upon e to the power, where x is this, okay, where x is basically this, e to the power x plus e to the power minus x, okay, considering this as your x. Now this will tend towards 1. You can see that at t tends towards 0, this x value will tend towards infinity. So e to the power minus infinity values, they will tend towards 0. You will have e to the power x upon e to the power x. So tan hyperbolic of this will tend toward 1. So therefore your magnetization will tend towards n times mu b, which will be your saturated saturated magnetization. Okay. Now similarly, as t tends to infinity, now you can see that this tan hyperbolic mu b h by kbt. Again, just see the definition of tan hyperbolic x. So basically, as t tends to infinity, this x value will tend to, if t is tending to infinity, basically x is tending to infinity. Okay, this x is tending to infinity. Here this x will be tending to 0. Okay, which is e to the power x. This is your x minus e to the power minus x upon divided by e to the power x plus e to the power minus x. So x will tend towards 0. If x tends towards 0, basically e to the power 0 will tend towards 1. So it will be 1 minus 1, 0. So this will tend towards 0. Okay. Therefore, your net total magnetization will tend towards 0. Now the other thing was we have to find this magnetization saturation for a particular value of n. Okay, number of spins per unit volume. So let for n equals to 3.7 into 10 to the power 28 per meter cube, the zero temperature magnetization saturation, zero temperature saturation magnetization hence, so this ms we know this is basically n times mu b. Just put the value of n 3.7 10 to the power 28 and value of mu b Bohr magneton. Okay, so this is per meter cube and Bohr magneton is 9.274 into 10 to the power minus 24 joule Tesla inverse. So what you will get, ms is equals to 3.43 into 10 to the power 5 ampere per meter. Right. Okay, so this will be our saturation magnetization. Now, so why this is happening? So as I said also, let me just write it as well. Basically at zero temperatures, so this is basically the physics part, because of which we directly write our answer without even going into the formula, without going into the mathematical formula for the magnetization. Now at zero temperature, the spins are perfectly aligned by an external field because there is no thermal energy available to randomize the spin directions and thus increase the entropy. At infinitely high temperatures, there is enough thermal energy to randomize the spin directions give external magnetic field. So this is what I discussed in the start of this part. Okay. So at high temperature, it can complete. There will be thermal energy that will completely randomize the spin direction, and so even in the presence of an external magnetic field, the net magnetization will be zero. Alright. So this was our part D. Now the part E is. So in this part E, what does the relationship between M and H reduce to for weak fields H tends towards zero, and what is the expression for the susceptibility in this case, and how does it depend on temperature? Calculate the numerical value of the susceptibility at room temperature. Okay. So this is part D. In part D, we need to find this M versus H relation for H tending towards zero in the smallest. So basically, what we have. So basically, we have this tan hyperbolic formula: e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. And as we know, as x tends towards zero, basically if your x is tending towards zero, we can also say that this tan hyperbolic x will tend towards x. Okay, so as you see, it will tend towards zero. So basically, for a small value, not exactly zero, but like very small, close to zero, if x is very small, so I have written it as x tending towards zero, but basically you should consider it like we are going to some epsilon value. Basically, okay, let me just say epsilon value actually, yeah, where this epsilon is very small, very small. Take epsilon tends to be zero. Alright, consider so because this will otherwise you might get confused from this one, I guess, where we have actually t tends to infinity case where I tend x tend towards zero. So we are not tending it to be to zero, but let's say our x is tending towards a very small value, epsilon value. So why this happens? Because you can expand this tan hyperbolic as 1 plus x square by 2, alright, and so on. Okay, do the expansion of this exponentials as is minus x whole square by 2 and so on. Just a minute. Alright, and then similarly just do this expansion here, and minus x plus minus x whole square by 2 and so on. So and as x is very small, you can ignore the higher order values basically. So this tan hyperbolic as if x is very small, so what will happen? You will ignore the higher order terms, which are x squared terms. So ignore the higher order terms. So you will get 1 plus x minus 1 minus x upon is 1 plus x plus 1 minus x. So so if you see this, so this will be basically 1 we cancel out, and x plus x will be 2x divided by in the denominator we will get 2, so we will get x. So basically your tan hyperbolic x will tend towards x in the limit x is a very small value. Okay, let's say some epsilon value which is tending towards 0. Alright, so basically your tan hyperbolic x will tend towards 0. So we can say, so as x tends towards epsilon, okay, some very small value where epsilon tends towards 0, tan hyperbolic x tends towards x. So therefore, as h tends towards 0, okay, as we are saying, okay, so does it say h tends towards 0 or v? Okay, yeah, we can say, okay, so you can say h tends towards epsilon as well, just to not get confused that you have to put h tend towards 0, but sometimes if it is written h tend towards 0, it means that you are tending towards a very small value. So let me just say that, okay, as x tends towards 0, this tan hyperbolic x tends towards x. So basically, I guess there is no confusion. Basically, if it is written that x tending towards 0, it means we are tending the x is not, you don't exactly put it 0, you actually put it to be a very small value, and then you can use the expansion. I guess in the last part, yeah, I said that like it will tend towards 0 because it equals 0, but it's better to do the expansion and see that basically tan hyperbolic x will tend towards x. Okay. So and t tends to infinity means we are putting basically here we are doing t infinity, t tends to infinity, so it was almost exactly 0. So that's why this magnetization was going to 0 as t tends towards infinity. While in this case we are saying that x is tending towards 0, but it is not exactly like it is close to 0, but not that close. So you don't just put 0 there. So that's why it will tend towards x value. Alright. So hopefully there is no confusion in that part. Okay. So therefore, so this tan hyperbolic x tends towards x. Therefore, as s tends towards 0, very small field. Okay, so basically very small field. Let me just write like this. Basically, what will happen for small applied magnetic field? Therefore, this nu b h by kbt, okay, this will tend towards nu b h by kbt. Alright. Let me just write it as this sentence. Alright, so the magnetization. So now the magnetization. So this m will tend towards n times nu b square h upon kbt. So the susceptibility is phi equals to m by h is equals to n times nu b square by kb 1 by t. Okay, and susceptibility is given by m by h, so you can just that will be equals to n nu b square by kb into 1 by t. So it is we can see that it is inversely proportional to t here, and that is the Curie law. Okay, if you remember, this is the Curie law. Okay, this is Curie law. This is Curie law, Curie's law. So we can see that since this is the Curie's law, so our system is basically acting like a paramagnetic system. That is the susceptibility is inversely proportional to temperature and diverges only as t tends towards 0. Note that this is the Curie's law. Now then we have to find this value at room temperature. So at room temperature, when T is equals to 300 Kelvin, okay, now in dimensionless unit, so basically now we have to write, if I have to write in dimensionless unit, so this is generally in the CGS units, this formula is, but if you have to write it in the, so your susceptibility will have some dimension, this we discussed in the last session as well. But if you write everything in the SI units, if you want to put everything in the SI unit, then your susceptibility becomes dimensionless units. Or the SI units. Basically, these are the SI units, and to make it the SI units, what you have to do, you have to multiply it by mu naught as well, which is the magnetic permittivity of the vacuum. So so you have to multiply it by that as well, this constant mu naught, to do the calculation in SI units. Okay, then just put all the values which are given to you. Here n is given to you as 3.7 into 10 to the power 28 per meter cube. So basically, okay. So you have to your formula just changes if you have to do it in SI unit. Minus h per meter into mu b equals to 9.274 into 10 to the power minus 24 joule per Tesla. Kb is 1.381 into 10 to the power minus 23 joule per Kelvin, and temperature is given to you as 300 Kelvin. So if you just put all this value in, you will have your susceptibility as 0.000965. Okay, and here we can see that this susceptibility is positive value, and since basically because there is an inversely proportional to T, so we can see that our system is basically paramagnetic. So just a small note about it. The behavior described, so the behavior described by this non-interacting. So basically in this problem we have seen that it's a non-interactive. We have considered a 3D non-interacting spin system. So the spins were not interacting with each other; they were interacting only with the magnetic field and the temperature as well. So by this non-interacting spin system, okay, the behavior described by this non-interacting system is paramagnetic. The system shows Curie's law. Behavior and there is no phase transition to a magnetically ordered state. Alright, so basically the magnetization, as you have seen, it will be a maximum magnetization at t equals 0, and then it will just fall down. Okay, so there is not like any magnetic ordering that is happening at any temperature. In order to now, but if we want this magnetic order, so in order to describe ferromagnetic behavior, we would have to add interactions to our model. The interactions would have to be such that the energy of the system was lower than neighboring spins system was lower than neighboring spins. spins were aligned parallel to each other compared to when they were not aligned at all or had some other for example anti-parallel alignment. Alright, so basically if you have a non-interacting what we have seen is that if you have this if we have this 3D spin system which are non-interacting, a system of non-interacting spins, then their behavior is going to be similar to a paramagnetic systems, and that we have seen that if we calculate this magnetic susceptibility in the case of low magnetic field, it will be inversely proportional to T, which is the Curie's law, and thus the system is paramagnetic. And if we want to include make this ferromagnetic system, we want to make a system of this spins which shows ferromagnetism, then we need to add some interactions to our model, and we have to add those interactions in such a way that the energy of the system should decrease when the neighboring spins are aligned parallel to each other, as compared to when they are not aligned at all, or they are aligned in some other fashion, like in some anti-parallel way. Right? So that's how we can make this ferromagnetic system out of this 3D spins, by including certain kind of interactions which favors the parallel alignment of the neighboring spins. Alright, so this was our problem number 1. So let's go to problem number 2. Okay, so problem number 2 is, consider a system of two particles at temperatures T tends to infinity. Each of them consider a system of two particles at temperatures T tend to infinity. Each of them can occupy three different quantum energy levels, having energies 0, epsilon and 2 epsilon, and both of them cannot occupy the same energy level. Then what is the average energy of our system? Alright, now since both the particles cannot occupy the same energy, level, and there are three energy levels. The partition function is given by. So basically what is given in the problem is that basically you have three options. Okay, so you have two particles. For energies you have three options, but it is given that none of the at any time those two particles cannot have the same energy. So basically if you have to distribute this three energy among these two particles, the formula is 3C2. Okay, so you have to make packets of 2 from this three energies. Okay, so that will be the different combination, and this is, as you know, it is equal to 3. Okay, so the energy of the particles basically will be either 0 epsilon or, okay, so this will be the set 0 epsilon. Let me just make this set with blue color. So basically the set of the energy could be, the particles could have 0 epsilon energy, 0 2 epsilon energy, or it could have 2 epsilon epsilon comma 2 epsilon energies. Okay, limitless T, each of them can occupy three different quantum energy levels having energy is this, and both of them cannot occupy the same energy level. Okay, and these particles, okay, so and there will be like no epsilon and 0 and other combination that you might think, okay, like epsilon comma 0 could also be combination, but that is not the case, because both the these are just two particles are there, so either one has 0, one has epsilon, and if one has epsilon, one has 0. Okay, if you take this epsilon comma 0, then that will just give you the same system. Okay, so your system could have so that is not what we are going to consider. Okay, so we will just consider this three set of energies. So your partition function, that will be equals to, we know SK partition function is given by e to the power minus ei times, you can say beta, where beta is equal to 1 by kBt. Okay, so this will be equals to this will be equals to, our energy would be e to the minus beta times the, okay, now net energy would be one case will be 0 plus epsilon, then e to the minus beta 0 plus 2 epsilon, and plus e to the power minus beta epsilon plus 2 epsilon. Okay, so your z partition function will be given by e to the power minus beta plus beta minus beta epsilon plus e to the power minus 2 beta epsilon plus e to the power minus 3 beta epsilon. Okay, so this is our partition function. We have to find the average energy of the system. So first we need the partition function, then the average energy is given by, so the average energy, let's say, okay, this will be given by summation of I ei e to the power minus beta ei by the partition function z. So that will be equals to, our energy could be epsilon, it will be e to the power minus beta epsilon, plus the energy could be 2 epsilon, it will be minus 2 beta epsilon, and energy could be 3 epsilon. Okay, this will be energy epsilon, epsilon, 2 epsilon, and the net energy is 3 epsilon. 3 epsilon e to the power minus 3 beta epsilon divided by whatever the z is. Now it is considered system, and we have to consider this limit as well. It is given that we have to consider temperature limit T tends to infinity. Now in T tends towards infinity, or what we can say is beta will tend towards 0. Beta is 1 by kBt limit. It is 1 by kBt. So in T tends to infinity or beta tends towards 0 limit, what you are going to have is basically your average energy. So what will happen, as beta will tend towards 0, each we can take that e to the power x terms, we can take them as we have seen in the previous problem as well. As t was tending towards infinity, we have taken this e to the power, you can just put the value e to the power 0. So basically this average energy will be epsilon plus 2 epsilon plus 3 epsilon divided by z, and z will also tend towards 3. Okay, because each of these epsilon terms will tend towards 1. Okay, so this will be equals to 6 epsilon divided by 3. So the average energy comes as 2 epsilon. Okay, so this was okay. Okay, any doubt in this problem? Okay. Okay, let's go to problem number 3 then. So now problem number 3, what is as is now what is the value of the product s1 vector dot s2 vector for total spin s equals to 2 for of 2 spin 1 particles. Okay, so we are given 2 spin 1 particles, so each of the particles they have capital S. Spin 1 particle means each of the particle they have s equals to 1. All right, and it is given that the total spin of those particles is 2. So now since, and then we have to find this product. Now we know since s vector is equals to s1 vector plus s2 vector, and also remember that s vector square on the cat s will be s into s plus 1 cat s. So basically, so now what we have s vector square is equals to basically you have to do s1 vector plus s2 vector whole square. This will give you s1 vector square plus s2 vector square plus 2 times s1 vector dot s2 vector. Now here where this capital S is the capital S is total spin. Now given that s1 vector and s2 vector add to a total spin equals to 2, this s vector square, which is basically s1 vector plus s2 vector whole square, this is basically so this will be equals to s into s plus 1, and total spin s is given as 2. Okay, so this will be equals to 2 times 2 plus 1, that will be 6. So x vector square value will be 6. Now similarly here now this s1 vector and s2 vector are spin 1, these are spin 1 particles. Okay, since the or you can just say since the particles are spin 1 particles, and now since the 2 particles are spin 1 particles. Okay, so they spin 1 particles, that means s1 vector square, which is really equals to s1 times s1 plus 1. So s1 and s2 are basically, it means that s1 equals to s2 equals to 1. So you have 1 plus 1 equals to 2. Similarly, s2 vector square will be equals to s2 times s2 plus 1. That will be 1 plus, times 1 plus 1 equals to 2. Okay, so basically now we just have to put the values in. Okay, so we have s1 s vector square is equals to s1 square plus s2 square plus 2 times s1 vector dot s2 vector. Now s vector square we have found it is 6, and each of them, these are 2 plus 2 times s1 vector dot s2 vector. So from here s1 vector dot s2 vector will be equal to 6 minus 4 will be 2 divided by 2 that will give you 1. So this is our answer. So the product is s1 vector dot s2 vector, that will be equals to 1. Alright, any doubt in this problem? Okay. Alright, so let's go to our next problem, problem number 4. Okay, so now problem number 4 is, what is the correct wave function for 2 electrons containing spatial and spin parts of wave function for total capital S equals to 1 and ms equals to 0. Okay, so again we have 2 electrons. Okay, 2 electrons with these means these are spin half particles. Okay, remember that these are spin half particles. Okay, so Okay, so S1 equals to, you can say S1 equals to S2 equals to half A. Instead of saying that these are spin-half particles, it is said that they are electrons. Electrons, we know these are spin-half particles. Now we have to find the correct wave function for two electrons containing special and spin parts. Okay, and so means we need to take care of the antisymmetry as well, because we are talking about electrons, they are fermions. So we have to, the wave function must be antisymmetric. And for that it is given that total S is equals to 1 and MS equals to 0. Okay, so from that we need to find whether the spin part is symmetric or antisymmetric, and accordingly we will make the special part. Alright, so here the overall wave function for electrons must be antisymmetric, given that S equals to 1 and MS equals to 0. Now this, which represents symmetric spin part of the wave function which is a triplet and antisymmetric special part. Okay, so from S equals to 1 and MS equals to 0, what we can know that for S equals to 1, okay, we know that in that case so this is a triplet state. Okay, the spin state is going to be a triplet state, as we have seen in the lecture. For S equals to 1 we have MS equals to 0, and the this antisymmetric spin state comes when for the singlet case, when we have capital S equals to 0. This is capital S equals to 1 and MS value is given 0, which represents symmetric spin part of the wave function triplet, and antisymmetric spatial part, so that the overall wave function is antisymmetric. The spatial part of the wave function is so here from capital S equals to 1 itself, we know that this will be one of the triplet state. Okay, so that's why from we know that we have to make an antisymmetric part of the spatial, and then you will need this MS equals to 0 value to know the exact whatever your spin part is. Okay, because it could be either for capital S equals 0 you can have MS equals to -1, 0 and +1. So it could be any of these symmetric spins, but it is given that MS is equals to 0, so you know that what is the spin part. Now the special part of the wave function is, then the special part of the wave function will be 1 by under root 2a psi r1 psi b r2 minus psi a r2 and psi b r1. Okay, you can check it that if you just interchange r1 r2, there will be a minus sign. So this is antisymmetric. R2 psi b of r1, and the spin part is spin part. We are given capital S equals to 1 and MS equals to 0 is given to you. So it will be 1 by root 2. It means one will be up down plus down combination. Okay. So the overall wave function is by 2 psi psi A R1 psi B R2 minus psi A R2 psi B R1 times spin up down plus down. Alright, so this is our answer. Okay. Any doubt in this problem? Okay, so let's just move on to problem number 5 then. Okay, the Hamiltonian, okay, in problem number 5, what is given is the Hamiltonian for Heisenberg model is H is equals to minus half summation over ij, jij, si vector dot sj vector. Then we have to write the above Hamiltonian in terms of the si plus minus and siz and sjz. Alright? So let's just do this one. So we have our Heisenberg Hamiltonian. Okay. You don't need to know the Heisenberg model. Yeah, I guess that will be taught in this week 9, I guess. Maybe in week 9 the Heisenberg model will come. But basically we know this problem is just related to basic quantum mechanics. Okay. So we know that it is jij si vector dot sj vector. Okay. So now we know that basically, so we just have to take the dot product. So if you take the dot product, this will give you jij six sjx plus siy siy sjy. Let's just put x. Okay, otherwise it will be then siz times sjz. Okay, this will get now. Basically, we know that. So this you need to know for this problem. The x component of this spin moment, it is given by si plus. So these are this plus and minus. These are your ladder operator kind of like you have for the, if you have this is from the quantum mechanics. So you have these ladder operators for angular momentum operators in quantum mechanics. Okay, which are si plus and si minus. So in case if you don't if you have not seen them or if you don't remember them, I would recommend going looking into any basic quantum mechanics book. Okay. So basically this six, the x component angular momentum, spin angular momentum, that is given by this divided by 2. Similarly, your siy, and your siy will be given by si plus minus si minus divided by 2. Okay, so you have to use these two formulas here. We have minus half, so h will be equals to minus half summation over ij, jij, si plus si minus divided by 2 times ha plus ha minus divided by 2 plus si plus minus si minus divided by 2 iota and si plus sj plus. Okay, this will be sj plus and this will be sj plus minus sj minus divided by 2 iota plus whatever it is in the z direction siz dot sjz. So now here, so let's solve this part first. So if I just put it like this. Okay. So let us solve this part first. So to solve this part, we have Si plus Si minus divided by 2 dot product Si plus Sj plus Sj minus divided by 2. So this will give you Si plus Sj plus Si plus Sj minus plus Si minus Sj plus. Okay. So as you remember this, the commutation relation, like that you can't. AB is not equals to BA if A and B are operators in quantum mechanics until unless the commutation of A and B is 0. So in this case, this I and J. So right now you should write them in this fashion only. Si minus Sj plus, and then you will have Si minus Sj minus. Okay, divided by 2. Although I guess for Ij case these are like on different atoms, the Si plus and Sj minus, they will commute with each other, but I just write it in this form. Okay, this whole divided by 4. Sorry, divided by 4. Okay, we have this, and then let's just take this red part as well. Let me just show you the red. Okay, so we have this part, and then you have this part as well. Si plus minus Si minus divided by 2 iota, and Sj plus minus Sj minus divided by 2 iota. So that will be equals to that. Okay, so if you multiply 2 iota, that will give you minus 1 by 4. Let me just keep this minus 1 by 4 outside, and we will have, it is multiplied, we will have Si plus and Sj plus. Then similarly I will have minus Si plus Sj minus Si minus Sj plus and plus Si minus Sj minus. Okay, so here you can see that there is a minus sign here because of iota. So let me just bring this minus sign inside. So I will have minus, plus, plus, and minus. Okay, and let me just divide it by 4. So that will be, this will be our. Okay. So now these two terms, red and blue terms, we have to add, and here we can see that basically these two terms will cancel out with each other, and similarly these two terms will cancel out with each other. Okay, and because of they are not commutable, the commutation is not 0, so that's why you have to write them in this fashion, like Si plus Sj minus is not equals to Si minus Sj plus. Okay, so if we write it, so basically our Hamiltonian now H will become minus half summation our Ij, Gij, just sum these two. So you will have twice of this Si plus Sj minus plus Si minus Sj plus from red and blue terms. So if I do here, it is Si plus Sj minus plus Si minus Sj plus divided by 2 plus Si C Sjz. Okay, so this is our final answer. We have changed our Hamiltonian into the Hamiltonian now is in terms of this Si plus Sj, Si plus plus minus and Sj plus minus operators, and the Siz and Sjz operators. Any doubt in this problem? Okay, so this was problem number 5. So let's move to problem number 6 then. Just 1 minute. Okay, let's continue. So this is our problem number 6. So in problem number 6, what we have is some organic molecules. They have a triplet S equals to 1 excited state at an energy Kb delta above a singlet S equals to 0 ground state. Okay. So we have to find an expression for the magnetic moment, average magnetic moment mu in a field B, and we have to show that the susceptibility for T much greater than delta is approximately independent of this delta value. Alright. Okay, so basically what is given is to us is that we know there are going to be 3 triplet states are there. Okay, and what is given is that we have our singlet state, which is a single singlet state S equals 0, that is your ground state. And okay, so this is your ground state, and above that ground state you have your triplet state, and it is given that some organelle have a triplet state excited at an energy Kb delta. So basically the energy difference between them is Kb delta. Okay, Kb delta. Okay, sorry, and so the separation between these triplet state. Okay, just 1 minute. So basically, what problem is given is that basically you have your ground state. Okay, you have your singlet state, ground state, and at a distance Kb delta, you have your triplet state, which are going to be 3 states. Now we have to find the expression for the magnetic moment in a field. So what will happen? Initially, these 3 triplet state will have the same energy, But when you will apply the magnetic field, they have different ms value, and as we have seen that this energy basically comes as minus nu times h, or you can say nu times b as well. That is just the difference is just a constant. Okay, so and this mu is dependent on your minus some ge times nu b times ms. So for different ms value you will have different energies. Okay, so depending on that you will have different so these three will not remain degenerate. You will have three different energy levels. Okay, so that is the brief description of the problem. So let's solve this now. So first part, we have to find the average magnetic moment in a field B. Now here first we know that the relative occupancy probabilities are, so for energy E, so if your energy is E, then the probability of the system of a particle having that energy is given by minus beta E by kBT, and here this energy E is basically equals to this epsilon naught energy. Okay, whatever your epsilon naught epsilon energy is, this is okay, epsilon energy. Okay, so that will be your here this energy will be some so where this energy E will be basically equal to some epsilon naught, let's say some epsilon naught minus nu times ms times b. Okay, this will be actually it will be plus ms, because we know that the magnetic moment along the so as we have done in the first question, the magnetic moment along the direction that is given a minus mu times ms. Okay, if you consider each having the magnetic moment mu b instead of mu b, if you consider mu. Okay, so depending on your ms value, this will be different. Okay, so just a correction here. Okay, so this is epsilon naught plus mu ms times b. Okay, and here this so this is for the singlet case. For s equals to 0, this epsilon naught equals to 0, and then for s equals to 1 cases, this epsilon naught, let's say, is equals to some epsilon value, and that is equals to kb times delta. Okay, so because of this if we see these energy levels, just a minute. But yeah, but this is right actually. We have to take there's a minus sign for the magnetic moment. It was correct. So if it is a minus sign, then you have minus of mu vector dot b vector, basically that's your energy. So and you have a minus sign, so your energy will be mu ms times b. Okay. So basically now the energy levels, basically what you have is you will have 4 energy levels. One will be for your s equals to 0, okay, and others will have s equals to 1. This will have s equals to 1, and let me just write it with blue. This will be your s equals to 0. This will have s equals to 1 and ms equals to with the lowest energy minus 1. This will be S equals to 1 and ms equals to 0, and this will be S equals to 1 and ms equals to 1. Alright, so the energy value, so the basically energy if you have to calculate. Now here the energy will be just equal to, there is no, let's say, some ground energy, times ms is equals to 0 plus nu and ms equals to 0. Yeah, ms equals to 0, ms equals to 0. So okay, so this coming from basically the energy, this energy, because of magnetic field, you know, it will be minus mu vector times B, and mu vector will be equals to minus of GE. Let's just say we are not considering GE here, we are just considering some GE times nu B is some nu, it is some GE times nu B here, times ms. Okay, so that's why the energy will be nu ms times B, it will be plus. Okay, because we are writing it in terms of ms value instead of the magnetic moment. If it was just in terms of magnetic moment, then it would be minus mu times B, but it is in terms of the ms value, so it will be for this. And then so the energy here will be just equals to 0, so our ground state energy we can take as 0. Then this energy will be some epsilon, because epsilon it is stated, it is the difference is Kb delta between the singlet and the triplet state. So before the application of field there is some Kb delta. Okay, so this is the Kb delta difference. Okay, and then all the other levels, the energy difference between them, that is coming because of the magnetic field. So this will be and Kb delta is equals to epsilon. Epsilon minus epsilon plus mu times minus 1 times B, so it will be epsilon minus mu B. This energy will be equals to epsilon plus mu times 0 times P, so it will be epsilon. And this energy for ms equals to 1, it will be ms plus mu times 1 times P, it will be epsilon plus mu B. Right? So the probabilities here, so the probabilities for these energy levels being occupied, that is given by, so we have to find the average magnetic moment. So so in the case each will have different kind of magnetic moment. Okay, they can have this 4 based on that they can have this 4 energy levels within the magnetic field, and each of the energy levels will have the probabilities. Now e to the power, we will write e to the power 0. So this, since this energy is basically e to the power minus beta times 0 by kBt, B times, it is B. 1 minute, it is e to the power minus beta E. Okay, so there is no 1 by kBt, sorry about that, it is e to the power minus beta E only. I don't know where kBt. Yeah, beta is equals to 1 by kBt already. Okay, so it will be e to the power minus beta times 0, so that will be equals to 1. This will be e to the power minus beta times epsilon minus mu B, this will be e to the power minus beta times, okay, let me just write here that this beta is beta is basically 1 by kBt. Sorry about that, I have written beta and 1 by kBt also. That's there. E to the power minus beta epsilon, and this will be just e to the power minus beta epsilon plus nu B. Alright. So these are the probabilities now. So the average magnetic moment. So the average magnetic moment. This average magnetic moment, that will be equals to mu equals to summation of I mu I e to the power minus ei by b, then aside in terms of beta only, so minus beta ei divided by the z, where z is our partition function. Okay, this is our partition function. Okay, so our z will be equals to where this mu I will be equals to minus of mu times mi, mu times ms. Okay, so this we know. Okay, so our magnetic moment is minus mu times ms, and the energy ei is basically equals to this epsilon naught. Okay, as we have written, epsilon naught plus mu times ms. Okay, ms times b. Okay, that we have already found. So first we will write our z partition function. So z will be equal to summation of I e to the power minus beta times ei. That will be equal to we have energy e to the power 0. It is just sum of these probabilities. It will be 1 plus e to the power minus beta times epsilon minus nu b plus e to the power minus beta epsilon plus e to the power minus beta epsilon plus nu b. Alright. Then the average magnetization, that will be equals to, okay, so first we will have the ground state, which has the magnetic moment to be ms equals to 0. So it will be 0 times 1 plus, next we will have the magnetic moment. The magnetic moment is given by minus mu times ms equals to minus 1, so it will be plus mu times e to the power minus beta epsilon minus mu b. Okay, then we have ms equals to 0, so that will be 0 times e to the power minus beta epsilon, and then we have ms equals to 1, so the magnetic moment will be minus mu times e to the power minus beta epsilon plus mu b, divided by whatever our partition function is. Okay, so this point is clear, right? So average magnetization is summation of mu I, and mu I is given by minus mu times ms. So for the ground state, ms is 0, then this is for ms equals to minus mu. Okay, let me just write it. This is basically for ms equals to minus 1. Okay, we have ms equals to minus 1 at the bottom. So minus 1 will give you plus mu. So mu times the probability, is e to the power minus beta epsilon minus nu b. Same thing for ms equals to 0, and then for ms equals to plus 1, magnetic moment is minus mu, and the probability is e to the power minus beta epsilon plus mu b. Alright, so our average magnetization is basically given by mu, I can take common, e to the power minus beta epsilon minus nu b plus e to the power, sorry, there will be this will be minus e to the power minus beta epsilon plus nu b, this whole divided by the partition function z. Okay, so this is our average magnetic moment. Right, so this was our part A. Find the expression for the magnetic moment in a field. So what we expect the magnetic moment to be of each of the spin, okay, on an average, basically magnetic moment on average magnetic moment, you can say. Now show that a susceptibility for capital T much greater than delta is approximately independent of delta. Okay, now at high temperatures, this capital T, which basically means so at high temperatures, which means temperature is much greater than this delta value. Okay, delta is kb times delta. That means basically you can say that kbt is much greater than kb times delta, which is the difference between the singlet and the triplet states. Okay, or that we have said to be epsilon. That is, okay, we are writing it as epsilon. So kbt is much greater than epsilon. So this is the condition. So in this state, in this condition, we have to find the susceptibility. So first we can see that in this case kbt is much greater than epsilon, and in this case in e to the minus epsilon by kbt values. Now what will happen? Kbt is much larger than this, so this will tend towards basically what you can do, you can again do the expansion of this thing, minus epsilon by kbt. Okay, so as kbt is very large, this Sn by kbt will be a very small value, and so on. So so this epsilon by kbt is very small compared to 1. Okay, so that's why this e to the power minus epsilon by kbt, that can tend, that we can basically can tend towards 1. So this value is much less than 1. Okay, so so if you do this expansion, so all these terms, epsilon by kbt terms, these are very small, so we can just ignore all of them, and we can take that epsilon to the power minus kbt will be tending towards 1. So if we take that limit, what will happen to our partition function? So our partition function, that is given by 1 plus, okay, partition function was this. Okay, it is 1 plus e to the power minus beta epsilon minus nu b, 1 minute, yeah, e to the power 1 plus e to the power minus beta. Okay, so it is 1 plus e to the power minus beta epsilon minus nu b plus e to the power minus beta epsilon plus e to the power minus beta epsilon plus mu b. Okay, so this I can write as 1 plus e to the power minus beta epsilon times e to the power minus mu b plus e to the power minus beta epsilon and plus e to the power minus beta epsilon e to the power minus beta mu b. Okay, so in the limit, in this limit, that is for t, so for t much greater than delta, what we have shown that this epsilon e to the power minus beta, this tends towards 1 minus beta epsilon e to the power minus beta epsilon. So this is basically e to the power minus beta epsilon, where beta is 1 by kbt. So in that case, z will be 1 plus, put all the e to the power minus beta epsilon values to 1. You will get e to the power minus mu b plus 1 plus e to the power minus z will tend towards. Okay, let's say z tends towards this minus mu b. Okay, then I can write it as 2 plus, again what I will have is just do the expansion, minus mu b plus minus mu b whole square by 2 factorial and so on, plus expansion of 1 minute, it is 1 minus mu b and 1 minute, it will be e to the power minus mu b, and this is, sorry, this will be e to the power plus mu b. Okay, because minus minus we get beta times mu b, it will be plus, so 1 will be plus and 1 will be minus. Mu b beta times mu b beta times mu b e to the power minus beta times mu b plus minus beta times mu b whole square by 2 factorial and so on. Okay, so here again basically, okay, so first what we have seen that beta by epsilon is very small, and again if you we can say that, okay, so from here we have seen that this epsilon by kbt or this beta epsilon is much less than 1 because temperature is very high. Now similarly, since temperature is very high, although we have like nu b here instead of epsilon, but nu b is also not going to be very very large. These are also a small value. So we can see that we can say that this beta and mu b terms, they are also very small. So we are not gonna ignore the first order terms of beta and mu b, but we can ignore the higher order terms like these square terms. Okay. So since we are at high temperatures, ignore beta to the power n terms with n greater than greater than equals to 2, or greater than equals to 2. Okay, for n greater than equals to 2, we will ignore those terms which have beta to the power n terms, because the temperature is very high, so beta must be tending towards 0. Or tending towards a small, quite small value. So we can say that our this partition function z will tend to 2 plus 1 plus mu beta mu b, okay, plus 1 minus beta mu b. That's why our partition function, basically our partition function z now, because plus minus we cancel out, our partition function z tend towards 4. So now our we have to find, remember we have to find for the susceptibility. So first we are finding how our average magnetic moment, where our average magnetic moment is tending towards, and then you know that the net magnetization will be whatever the density of the magnetic spins is times this average magnetic moment, and then just divided by the magnetic field. That will be your susceptibility. So our average magnetization, that will be equals to, so it was mu e to the power minus epsilon minus mu b by kBt minus e to the power minus epsilon plus mu b. Okay, I have written by kBt. Let me just write it in terms of beta only. Beta times epsilon minus mu b and beta times epsilon plus mu b divided by z. So now at high temperature, that is kBt is much greater than epsilon, average maximum will tend towards mu, again e to the power minus beta epsilon, so basically e to the power minus beta epsilon will tend towards 1. Okay, so we will have mu e to the power mu b by kBt minus e to the power minus mu b by kBt divided by z. We have already found it tend towards 4. Then again what we have done earlier, basically you will do the expansion and then you will ignore the square order terms which have a power more than why I'm writing why I'm writing 1 by kBt again and again. Let us write it as kBt. Sorry about it. So basically you will have 1 plus you will get 1 plus beta nu b okay from this okay, so what you will get 1 plus beta nu b minus 1 minus beta nu b divided by 4. So your average magnetic moment basically will tend towards maybe 2 minus you will get plus, you will get 2, so basically you will get mu square beta b by 2. Okay, so your net and now so this you should remember. So basically susceptibility, that is basically given by capital M by B if you are writing in CGS units. So this I have discussed earlier as well, so but now I will just let me just formally write this. So the susceptibility, that is given by capital M by capital B in CGS units, and it is in the SI units, it is given by mu naught M by B in SI units. Okay. Okay. So this is you should remember. Change it to mu naught somewhere, I guess. In this first problem, we actually change it to mu naught, right? The formula was M by H. Okay, yeah. The formula was M by H in that case. We have to write the mu naught here also. Yeah, there also we have to change it a little bit. Okay. Okay, so this is the formula. Basically, in CGS unit it is M by B, and in SI unit it is mu naught M by this. Okay. Okay. So now we have to find the susceptibility. So we are gonna use this CGS unit formula. So we are just using capital M by B now. Capital M by B here. So and now we know that will be equals to basically okay, it is let's say this is per unit volume. So let me just write it as small n only. Mu by capital B, where this n is the total number of magnetic moments. Per total number of magnetic moments per in the system, let's say per unit volume. Okay. So that will give you your magnetization. Now at higher temperatures, which is in our problem is kBT much greater than epsilon energy. The sky now will tend towards, so our mu is tending towards, okay, the mu is tending towards nu square beta B by 2. So this will tend towards n times whatever your energy average u if you put in, it will be nu square. Basically B will just cancel out. Okay, B will cancel out from here. So n nu square by beta, and beta you can write it as by kBT. So I am just writing it as 1 by kBT. So this is your final answer. So our susceptibility will go as 1 by T. Okay. Any doubt in this problem? Just 1 minute. So let's move on to the next problem. So this is problem number 7. So here we have to consider a two-level system. Okay, what do you give? We have to consider a two-level system where the two energy levels are at delta and minus delta. Now determine the average energy and heat capacity for the system, and if the system has a random composition such that all values of delta are equally likely up to some limit delta naught, show that the heat capacity is linearly proportional to the temperature provided kBT is much less than delta naught. Alright. So first we have to find the average energy. So that's an easy part. So we know already know, okay, we have found it several times. Average energy is summation of I EI e to the power minus beta EI by Z, where Z is our partition function, and Z is given by summation of I e to the power minus beta EI. Okay, where beta is equals to 1 by kBT. Okay. Now here EI, it is just a two-level system, and there are two energy levels, delta and minus delta only. So our EI is basically just plus minus delta. Therefore, the average energy that I can write as will be equal to for delta e to the power minus beta delta plus minus delta times e to the power minus delta will give you a beta delta divided by the partition function, which is just e to the power minus beta delta and plus e to the power beta delta. Okay. So basically this gives you the average energy delta. You will have e to the power minus okay, let me just take minus delta common. So if I take minus delta common, then I will have e to the power beta delta minus e to the power minus beta delta upon e to the power beta delta plus e to the power minus beta delta. Okay, and as we know, the formula for tan hyperbolic x, that is basically e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. So this will be tan hyperbolic x. So average energy E will be equals to, that will be equals to minus delta tan hyperbolic so average energy will be equals to minus delta tan hyperbolic beta delta. Okay. So this will be our average energy. And okay, so actually I have done this problem in a different way. So so just because I have written like this, that kBT is equals to tau. Let me just write it like this because I have solved this problem in this fashion. So that is if you consider kBT as tau, so beta is equals to 1 by tau. So basically I will write this as tan hyperbolic delta by tau. Okay. So let us go with this one because I have solved this problem taking kBT because you have to take a differentiation with respect to t. So that's why basically I am doing this substitution here. Instead of beta, let's just call kBT as tau, and you will see why. So now the heat capacity C, that is basically we know that is because I have to do the differentiation with respect to temperature. You can do it in terms of beta as well. Okay, let's just do it in terms of beta only, maybe, because sometimes because beta is more generally we take. Let me just remove it. Just do it in terms of beta. Okay, so this is our average energy. So one part was to find the average energy, that is done. Okay. Now we have to find the specific heat. Okay, B is what heat capacity that we have to find. So that equals to D. Okay. Now you can write it as average energy is given in terms of beta. I can write it as just take the differential with respect to beta and d beta by dt. Okay. So here basically if you so here we have to do this differentiation. Now d beta by dt, which is just so this d beta by dt, it is just differentiation of 1 by kBt. Okay, beta is basically 1 by kBt. So if we have to differentiate it, it will be 1 by kb minus 1 by kBt square. Okay, so d beta by dt, that is just d by dt of 1 by kBt. So that is equals to 1 by kb d by dt of 1 by t, that will equals to minus 1 by kb t square. Alright, so this is a simple differentiation. Okay, and then we have d differentiation of d epsilon by d beta, and then this will give us, I will have minus delta times d by d beta of tan hyperbolic beta delta. Okay, so this is we have to do, and this you can further write it as, okay, let's say delta kBt square. Okay, this will be delta kBt square. Now this I can write, basically I can take it as d by dx of tan hyperbolic x times dx by d beta. Okay, where x is equals to beta times delta. Okay, so here this d by d beta of x, this dx by d beta, which is equals to d by d beta of beta times delta, that will be basically just equals to delta only. Alright, because delta is constant and d beta by d beta will be 1. So basically what we have heat capacity. Now C is coming as kb, I can write it delta by kBt whole square. Okay, delta by kBt whole square times what I have is d by dx of tan hyperbolic x. Okay, where x is equals to beta times delta. Now so basically let's just do this differentiation of d by dx of tan hyperbolic x. So if you have, so this differentiation d by dx of tan hyperbolic x, so it will be basically d by dx of e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. Okay, so one you will do different, so that will be equal to e to the power minus x, differentiate the numerator e to the power x plus e to the power minus x, then you will have a minus, numerator is whatever it is, differentiate the denominator, you get minus e to the power x plus e to the power minus x whole square times e to the power x minus e to the power minus x. Okay, so that will give you basically e to the power x plus e to the power minus x whole square, e to the power x plus e to the power minus x whole square minus e to the power x minus e to the power minus x whole square. Okay, so then again that is just a square minus b square terms you can see. So you can basically write this as e to the power x plus e to the power minus x plus e to the power x minus e to the power minus x, and e to the power x plus e to the power minus x minus e to the power x and plus e to the power minus x is 4 divided by e to the power x plus e to the power minus x whole square. So that basically will give you minus x to the power 2 e to the power x times 2 e to the power minus x okay sorry let me just not do this okay sorry sorry about that well let us not do it in this form okay yeah so, okay yeah okay sorry it was right okay sorry okay so we are here okay so you will get this e to the power x plus e to the power minus x whole square so basically you can see that what we are getting 2 upon e to the power x plus e to the power minus x whole square and this you know this is basically 1 by cos hyperbolic x square which will be basically yours sec hyperbolic x square okay so that means so I just yeah I just did this derivation so that you don't have to remember all the hyperbolic formula if you just know the hyperbolic formula for sin hyperbolic x and cos hyperbolic x that is fine and then you can make a tan hyperbolic x just sin hyperbolic x by cos hyperbolic x and then the other formulas the other things that you can do so d by dx of tan hyperbolic x is just equals to sec hyperbolic x whole square right. So we will just use this thing here. So our heat capacity now will be equals to what we have is Kb times delta by kBt whole square times d by dx will give us a sec hyperbolic x and x is basically x here is beta times delta or delta by kBt whole square okay so that's our heat capacity okay this is my heat capacity alright now let's go to the B part. Now the B part is if the system has a random composition such that all values of delta are equally likely up to some limit delta naught, show that the heat capacity is linearly proportional to the temperature provided kBt is much less than delta naught. Okay, so okay now the probability P delta times T delta that the upper level upper energy level lies between delta and delta plus d delta. Okay, so basically we have this ground energy. We have two energy level system, okay, which are at energy delta and minus delta, and the system has a random composition such that all the values of delta are equally likely up to some limit delta naught. Okay, we have to show that the heat capacity how that is changing. All delta values are equally likely to some limit. Okay, so basically what it is saying that for between the energy difference delta and delta plus d delta, let the energy level lies between them. That probability is P delta times D delta, and we are saying that refer to the midpoint as P0 of energy now that is so that probability that the energy level is between some delta and delta plus D delta, and it is said that up to some delta naught you just assume that all the energies are equal they are equally, basically it is given that they are at all values of delta are equally likely up to some limit delta naught. So we can say take that d delta will become d delta by delta naught. So each is so total energy is delta naught, some limit, and each one will have the priority to having that of occupation up to that energy will be 1 by delta naught. So in that case, if we calculate the average energy now, the total average energy now, so that will be equals to from 0 to delta naught. So here we have already calculated the average energy if we have just two energy levels at minus delta and plus delta, and now we are saying that this delta can vary, so we will take the average of that. So for that we have to take d delta p delta times whatever the average was in case of just one single value of delta. So from here what we will have integration 0 to delta naught d delta by delta naught, because they are equally likely, minus delta times tan hyperbolic delta delta by kbt. Just write it as delta by kbt. Now we have to find, we have to find in B part, we have to find for the heat capacity what is the, we have to show that the heat capacity is linearly proportional to temperature in the limit that kBT is much less than this delta naught value. So in that case, so we are considering that this delta value ranges from 0 to delta naught, and for each between this delta and delta plus delta, that this delta value will be that small delta value. That is just equal, so we have taken that probability to be 1 by delta naught. So the specific heat now, that will be now this du, the average u by dt. Okay. Then okay, and let me just take let us take this to be beta only, and have about beta times delta. Okay, and again what I can write it as d by dt beta du. This is du by d beta. Alright, and then again what I will get minus kb times t square, minus 1 by kb t square times d u by d beta. Okay, so that we have now. So what we will get is minus 1 upon kb t square will be there. There will be integration from 0 to delta naught d delta by delta naught, and let me just take this delta also. I will not take this delta out, this is not a constant now, but a minus will be, we can take out, and delta naught also I can take out. So I have taken out delta naught. We will have d delta, and I have so it will be d by d beta of tan hyperbolic beta times delta. So basically this we have already solved. If you have seen, it was that only. We will have d by d beta of tan hyperbolic beta delta. This we have already solved. So what we will have it will be delta times what we get for sec hyperbolic of this. So this differentiation kb t square integration from 0 to delta naught d delta times delta, you will get 1 delta square sec hyperbolic, okay, square beta delta. Okay, now so what we have is beta delta. So let me just multiply it by beta square and divide it by beta square. So if I do, okay, and here I can write this kb, and if I write kb above, okay, let me just write here actually. Okay, let's say if I am writing this as kb, this will become kbt whole square. Okay, and let me just write 1 by delta naught somewhere else. So what will happen if I write this 1 by kbt whole square is basically just beta square. So this we will have kb beta square by delta naught. Okay, now just take this, so I will take kb by delta naught here, 0 to delta naught d delta, take this b delta inside the integral, maybe we have b delta and a sec hyperbolic square b delta. Now let this b delta is equal to some x. Okay, so we will have d delta will be equal to dx by beta. Okay, so therefore what we will have our expected there heat capacity basically now will be equal to kb times delta naught, integration it will be from x will be from 0 to beta times delta naught. Okay, and let's say this x naught is equal to beta times delta naught. I will just write it as x naught dx by beta. It will be x square sec hyperbolic x whole square. Okay. Okay, we are out of time today, but we'll just solve this, complete this problem. Now here what we have is we have okay, the limit that is given to we have to find. Now we have to show that the heat capacity is linear proportional to temperature. In this limit, kBT is much less than delta naught. So here delta naught is much greater than kBT. Okay, that means delta naught by kBT is much greater than 1. Okay, which is basically beta times delta naught is much greater than 1. Or you can say that this x naught is much greater than 1, because x naught is basically beta times delta naught. So basically what we are saying is that the limit is x naught is much greater than 1. Okay, so we can just consider that and also the reason is that this sec hyperbolic square. So let me just write the reason. So the integrand is dominated by contributions from delta between 0 to 1 by 0 to kBT, because sec hyperbolic x decreases exponentially, okay, for large values of x. Okay, so sec hyperbolic x basically it decreases exponentially for large values of x. So for this whatever for x is basically some delta. So this is if delta is between some 0 to some kBT values, basically smaller values only. So basically if you are saying that this kBT is very large, okay, so basically the kBT is very small, so only up to this range this can go, and x naught is very large. So basically what we can do is we can write this approximate our heat capacity as kb, okay, kb times I will have delta naught times beta, okay, times you can just integrate, you can just approximate it to infinity, because sec hyperbolic x it just goes to exponentially less and x naught is a very large value. So we can just take this integral to infinity, approximate to infinity. It will be sec hyperbolic square x, and this integral, so that this you can basically check from internet. So this integral will come as pi square by 12. Okay, so and here beta is equals to basically 1 by kBT. So from here we can see that our heat capacity, it will be approximately equals to, it is 1 by kBT, so you have kb square pi square by 12 delta naught, which is some constant, times t, because beta is equals to 1 by kBT, and this is just a constant. So we can see that the heat capacity is directly proportional to T. Okay, so it is linearly proportional to our temperature. Okay, so this is what we had to show in this problem. Alright. Okay. And any doubt in this one? Okay. So this is problem number 7, and in next session we will continue with this problem number 8. Okay, we are already out of time. Any doubt in any other problem? Okay, so if there are no doubts, then we can end this session.